So, for this video, what I'm going to do is talk a little bit about how we can determine statistical power using information from two different distributions. So let's say that we have one distribution where our sample mean, or our mu actually, not our sample mean, mu, is 7. Okay, so we're talking about the context here is that Miller did a classic experiment where he was looking at the duration of short-term memory. How many pieces of information could you hold in there? And so we might be interested in finding out whether a particular sample mean of, say, 8 is likely to have been drawn from this particular population. And we can also say that sigma in this case is going to be 2, because he talked about finding 7 chunks of information plus or minus 2. So that's going to be our standard deviation. And so this is mu. And we have our sample mean. We need to have a sample size in order to get sigma sub m. So just to make this easy, let's say that our sample size was 25. Okay, so at this point, in order to calculate our statistical power, we also need to set our alpha level. And generally speaking, that's going to be 0.05. Alpha is 0.05. And we're going to do a two-tailed test. So in this case, we're going to section off someplace over here and someplace over here, and these little sections here are going to be our 2.5% each, because we have to divide our alpha value between the two tails. Okay, so now we figured out, okay, this is the 2.5%. We need to find the z-score that cuts off that 2.5%. And you can go to your z-table and look that up, but I happen to know, because we're doing z-scores here, that this will be negative 1.96, because I've used this so many times, and this will be positive 1.96. Okay, so now we know what our cutoffs are here, and then we have to find out for our second distribution where that mean is going to fit in. So the sample mean of 8 needs to fit in here somewhere. And so part of what we could do is say, okay, let's find out what that raw score would be with respect to the first distribution. So I'm going to take the second distribution away for a minute. We want to find out what the equivalent raw score would be for 1.96. So we know that x equals z times sigma plus the mean. Okay. But in this case, since we're using the standard error, then we actually need to compute that first. Sigma sub m equals sigma divided by the square root of n, which in this case is 2, divided by 5, because the square root of 25 is 5. 2/5 is 0.40. So now we get to substitute that in. So we get 1.96 times 0.40 plus 7, which is our population mean. And it will tell us what this raw score value is. So get our trusty calculator out, and we say 1.96 times 0.4 plus 7. So our raw score value for this cutoff then is 7.784. Okay. So now we know if we were to draw here is our second distribution. You've noticed that I've already put 8 on here, and we know that it has to be over here somewhere. So I'm going to go ahead and add this over the top. 8 up here somewhere. And we need to find out then where that cutoff then corresponds on this second distribution. So I'm going to take my pink marker here and say, okay, let's draw, oops, let's see, yeah, it does work. Draw this line in here. And we want to find this whole area, all of this, because this is going to tell us what our power is. So this area tells us what our power is. So now what we need to find out is, with respect to this mean of 8, what is the corresponding z-score for this 7.784? So here, I'm going to grab a different marker here. And I'm going to say, okay, I need to find the z-score. I'm comparing this 8, which is our mean, and then we are going to compare this particular score with it. So I'm going to say 7.784 minus 8, because it is below the second distribution's mean, divided by the standard error, which is 0.40. Okay. And actually, to kind of eliminate some of the confusion for you here, I'm actually going to take this previous piece of distribution away here. So I'm just going to pull that right out. So now we're really only working with the second distribution. And oh, you can't quite see that. So I'm going to actually come back and use the black. So this is what we're doing. 7.784 minus 8 divided by 0.40. And in this case, we're going to find this is going to be a negative number. So it's going to be a negative z-score. Okay, so we're going to find that you can do the calculations as well. It's negative 0.54. So we know that this corresponds to negative 0.54. So now we have to get out our trusty z-table and look up what is the area between mean and z, right? This is the area we want to find, and then we just add 50% to it, okay? So I'm going to put that 50% down here because we know that our power is going to be greater than 50% because this is a negative z-score. That's a good thing. So if you flip to Appendix B, then you can look that up in your z-table, and I am looking up 0.54 mean to z. And I find that mean to z is 20.54%. So it's 20.54%. So this is not the most accurate scale drawing here, okay, but this area right here is 20.54%, and I'm going to add that pink 50%. So we've got 70.54% as our power. And I can add back in this other distribution here. Remember, it needs to go right on top because that critical value is going to line right up there. And we find that we have 70.54% power. So the first half you do with respect to this first distribution, and the second half you do with respect to the sample distribution. And that's how you find power for a z-test.